Hello students, myself Dr. Khushboo Verma, and today I am going to discuss about the basic concept of coding theory. Before we start, you should know some basic definition of the coding theory, like what is alphabet, what is code, what is message, and what is code word. The alphabet of the in the coding theory can be represented by 0 and 1 only, and message and code word also both can be represented by 0 and 1 only. In first part of the coding theory, we will convert the message under certain encoding rule to the code word, and in the second half part of the coding theory we try to decode the code word under certain decoding rule into the message. If we did not get the message which we discussed earlier, then we can say this is a case of error detecting or error correcting. Here E is called encoding function, which is defined from BM to BN, where M is a tuple of the message and N is a tuple of the code word. And BM is called set of all message and BN is called set of all code words. And D is called decoding function, which is defined from BN to BM. The relation between N and M is N should be greater than M. If M is equals to 3, then set of message contain 2 raised to power 3 element, that is 8 unique element. The set of message B3 contain 8 unique representation of 3 tuple, which is generated by 0 and 1 only. Or we can say the cardinality of the set of masses is always be equals to 2 raised to power m only. And if n is equals to 4 like else, then we can say set of code word, that is B4 contain collection of all code words which is generated by 4 tuples. Now let us discuss one example here. Suppose 101101 is a code word with respect to the message under certain encoding rule E, and 101101 again same code under certain with respect to the message 100 under certain encoding rule E. Here both code word are same, but initial messages are different, which is not allowed here. That's why we can say this is error detecting case here. Now as we don't know which one is correct, the first one is correct or the second one is correct, that's why we are not able here to correct this code. But if we know the encoding rule, suppose it is E of A1 A2 A3 is equals to A1 A2 A3 A1 A2 A3 under certain rule, E100 is equals to 100 100 and 101 is equals to 101 101. Now we can clearly say that the first code is correct, but the second code is incorrect. Now that means this is the case of error detecting and as well as error correcting also. Now next very important definition is Hamming distance and Hamming weight. Hamming weight means number of non and zero entries in any code. Suppose x1 is equals to 110110. Now how many non-zero entries in this code is 1 2 3 4. That means Hamming weight of x1 is equals to 4. Similarly, number of non-zero entries in x2 is 110 1 and 1, that is 3. That means Hamming weight of x2 is equals to 3 here. Now next concept is Hamming distance. Number of position between two code x and y where the code word have different symbol is called Hamming distance. It is denoted by small d. Suppose we want to know the Hamming distance between code word x and y. Now we have to count how many places where we have different entries. Here 1 is same, 0 is same, 1 is same, 0 1 is different and 1 0 different. 2 places, that means this distance between x and y is equals to 2. Similarly, distance between y and z is what? 1 is same, 0 1 is one place where we have different entry, and 1 0 again second place, 1 0 is same, 0 0 same, 1 1 is same. That means again distance between y and z is equals to 2. Similarly, we can find the distance between z and x also. This Hamming distance definition is very important here. Based on this definition, we have two important statement of the theorem. Two important statement of the theorem related error detecting and error correcting. We can detect k or fewer error if minimum Hamming distance is greater or equals to k plus 1, and we can correct k or fewer error if minimum Hamming distance is greater or equals to 2k plus 1. For example, let suppose we have an encoding function which is defined from b2 to b6. That means set of masses contain a message of 2 tuple, and set of code word contain code word with 6 tuple, and which is defined as follows. And we have to find the number of error which can be detected and which can be corrected. Suppose the first code is x1, second code is x2, third is x3, and fourth is x4. Now we have to find the minimum Hamming distance. That means first of all we have to find the Hamming distance between among all. Now distance between x1 and x2 is what? X1 and x2, number of different entries is here, same, not same. First is in different, third place is different, and last place is different. That means distance between x1 and x2 is equals to 3. Similarly, distance between x1 and x3 is what? First place is different, third place is different, and fourth place is different. That means distance between first is different and second is same, so third place, and next is fourth place. That means total 3 places are different here. That means distance between x1 and x3 is equals to 3. Similarly, we can find distance between x2 to x3, x2 to x4, x3 to x4. Now minimum Hamming distance among all this is equals to 3. Now on the concept of this theorem, we can detect k or fewer error if minimum Hamming distance is greater or equals to k plus 1. That means 3 should be greater or equals to k plus 1, and after solving we get k should be less or equals to 2. The condition on k is k always be greater or equals to 0 here. That means we can detect 2 or fewer error here in this code. Similarly, how many error we can correct? Here we can correct k error if minimum Hamming distance is greater or equals to 2k plus 1 here. Here minimum Hamming distance is 3. 3 should be greater or equals to 2k plus 1. 2k is equals to 3 minus 1. K is equals to less or equals to 2. That means k is equals to less or equals to 1. That means answer is we can correct one error only. That means under this encoding rule, we can detect 2 or fewer error, but we can correct only one error here. Now let us discuss the next important thing, that is a generator matrix. Suppose we have an encoding function defined from bm to bn, where m and n are defined as earlier. Then generator matrix with respect to this encoding function is defined as this. This is a m cross n matrix, where I is a m cross m matrix and A is a matrix of m cross n minus m. This matrix is called generator matrix, and with the help of this matrix we can find all code word with respect to the each message. The relation between message and code word and generating matrix is B is equals to A into G, where B and A, here G is a matrix and B and A are the row matrix. Similarly, parity check matrix. Parity check matrix is also defined over generator matrix. Here the dimension of this parity check matrix is n minus m cross n, where n and m are defined as in generator matrix, and A matrix is also defined as in generator matrix, and this is identity matrix n minus m cross n minus m. And the use of this parity check matrix, with the help of this we can check the code words are correctly transmitted or not. For this, if B is any code word, if we multiply B code with H transport, if this is equals to 0, as this is a row matrix, this is also a matrix, if that means this resultant value is also a matrix. If this is a zero matrix, that means null matrix, then we can say the code are correctly transmitted. If BH transpose is not equals to 0, then we can say code are not correctly transmitted. Here the matrix multiplication is defined over addition modulo 2. That means addition modulo 2. This is the symbol of this matrix multiplication here. Now let me solve one question here. Given that G is a generator matrix, and we have to find all code word, minimum Hamming distance, minimum Hamming weight, how many error we can detect and correct here, parity check matrix, and we have to check the following codes are correctly transmitted or not. Let me start. So to solve this question, given that G is a generator matrix, what is the dimension of this? It is 2 cross M, 2 cross 5. This implies here M is equals to 2 and N is equals to 5. This implies G is a matrix. If we write the dimension of this generator matrix, then this become I should be 2 cross 2 matrix and A should be 2 cross N minus M is what? N minus M is 5 minus 2, that is 3 matrix, and finally this should be 2 cross 5 matrix. Now if we compare this matrix to this matrix, we find here this is the identity matrix and rest one is A matrix. This implies here A is equals to 1 1 1 and 1 0 1 matrix. Okay, and rest one is a identity matrix. Now first question is we have to find all code words. As we discussed earlier, if M is equals to 2, this implies, and N is equals to 5, this implies encoding function is defined over B2 to B5. This implies B2 contains cardinality of B2 is equals to 2 raised to power 2, that is 4. And what was that? That means B4 contain B4. This implies set of message B2 contain all possible 4 masses of 2 tuple which is generated by binary bit 0 and 1 only. What was that? 0 0 1 0 1 0 1 and 1 1. Okay, now as we know what is the relation between masses and code word and generator matrix is B is equals to A into G, where B is code word, A is a message, and G is a generator matrix. Now we have to encode. Now we have to encode this message with respect to this generator matrix. Now B1 is equals to 0 0 with respect to this G, that means 0 0, and we have to multiply this by 1 0 0 1 1 1 1 0 1 1, and will get, now multiply this row matrix to this matrix with respect to addition modulo 2. What will we get? 0 into 1 plus 0 into 0 divided by 2. What was the remainder? That is 0. Now 0 into 0, 0 into 1, that is 0, and divide by 2. What was the remainder then? We will get 0. Similarly, we can find the masses this. Now next code word, which is with respect to the 1 0, G is equals to, that means we have to multiply 1 0 to the generator matrix 0 1 1 1 1 0 1 1. What we get? Multiply this 1 into 1 plus 0 into 0, that is 1, divide by 2, and what was the remainder then? That is 1. 1 into 0, 0 into 1, that is equals to 0. 1 into 1, 0 into 0, that is equals to 1, divide by 2. What is the remainder then? That is equals to 1. 1 into 1 plus 0 into 1, that is equals to 1, that is equals to 1. And last 1 into 1, that is equals to 1, and 0 into 1 is equals to 0. 1 divided by 2, that is, and in that case we will get the remainder 1. Similarly, B3 is equals to 0 1 G, and after multiplication, what will we get? 0 into directly we can write here 0 into 0 1, that is 0 0, In this case 1 into 1, remainder 1. In this case 0 into 0, 1 into 1, that is again 1. In this case we will get 0. In this case we will get 1. And B4 is 1 1. G is equals to this 1 1 1. And in this case is again 1. 1 into 1. Now let's see, 1 into 1 plus 1 into 1 is 2, divide by 2. What was the remainder in that case? That is 0. 1 into 1 is 1, divided by 0, that is remainder 1. And in last case 1 into 1 plus 1, that is 2, divide by 2, that is equals to 0 here. So these are the code here. The first question is find all code words. That means with respect to the each message we get the all code word here. Now next question is minimum Hamming weight and minimum Hamming distance. Suppose this is equals to x1, this is equals to x2, this is equals to x3, this is equals to x4, and we have to find the minimum Hamming distance. Minimum Hamming distance between them. The distance between x1 and x2 is equals to distance between x1 and x2 is equals to what? X1 is this and x2 is this. What number of different places is 1, 2, 3 and 4. Similarly, distance between x1 to x3 is what? Distance between x1 to x4 is what? Distance between x2 to x3 is what? Distance between x2 to x4 is what? And distance between x3 to x4 is what? X1 to x3 is what? The x1 is 0 0 0 0 0 and x3 is this. Now let us compare. First is same place, second is different place, third is also different, fourth is same, and last is different. That means distance is 3. Similarly, distance between x1 to x4 is 1, 2 and 3 different places. And similarly, x2 to x3 is what? Different places, 1, 2 same, and यहाँ पे third is different. That means 3 places. And similarly, x2 to x4, x2 to x4, 1 1 is same, 0 1 is different, 1 0 is different, and last 1 0 is different, that is 3. And similarly, x3 to x4, distance between them, 1 1 is same, 1 1 is different, 1 1 is same, 1 0 0 1, and last, that is 4. Okay. Now this implies minimum Hamming distance is equals to 3 here. Okay. Now minimum distance Hamming distance is 3 here. Now how many error we can detect? Based on the theorem statement of the theorem, we can detect 3 or we can detect k error if 3 is greater or equals to k plus 1. This implies k should be less or equals to 3 minus 1. That means k should be less or equals to 2 here. It implies we can detect 2 or fewer error here. Similarly, how many error we can correct here? Based on the theorem, 3 should be greater or equals to 2k plus 1. This will give the value of k less or equals to 2k less or equals to what? 3 minus 1. This implies 2k is less or equals to 3 minus 1. This implies k should be less or equals to 1. And finally, we will get we can correct 1 error here. That means in the given question we can detect 2 or fewer error, but we can correct only 1 error here. Okay. Now next question is what? Next question is find the parity check matrix here. based on this generator matrix. Parity check matrix H is defined as A transpose and identity matrix whose dimension should be n minus m cross n minus m, and the dimension of the parity check matrix should be n minus m cross n, where A is what, which is defined as in generator matrix, which you calculate earlier. This A is given here. Write down this. Implies A should be A transpose and I is equals to what? 5 minus 2, 5 cross 5 minus 2 matrix, and finally 5 minus 2 cross 5 matrix. Finally this will become A transpose I of 3 cross 3 matrix, identity matrix, and 3 cross, this should be 3 cross 5 matrix. And when we write the value of A, what will we get? A transpose is what? 1 1 1 and 1 0 1, and then 3 cross 3 identity matrix 1 0 0 0 1 0 0 0 1, and finally this become 3 cross 3 matrix, 3 cross 5 matrix. This is the parity check matrix with respect to the given generator matrix. Now next question is what? Check the following code which are correctly transmitted or not, where A is 0 1 0 0 and B is 1 1 0 1 0. As we know, based on this parity check matrix, we know the relation between the code word and parity check matrix, that is, if H into B transpose is equals to 0, then we can say code B is correctly transmitted. If HB transpose is not equals to 0, not valid here. Okay, that means we have to check this matrix H into the given A transpose. If the resultant value is equals to 0 matrix, then we can say it's a correctly transmitted code, otherwise it's a error code. Okay, here A is 0 1 0 0 0 and B is given 1 1 0 1 0. Let me start to check here. 1 1 1 1 0 1 1 0 0 0 1 0 0 0 1, and what is the formula here? H into B transpose. As we know, B is what? B is a row matrix, then B transpose is what? Column matrix. Write this code in column format, 0 0 0, and multiply by this matrix. What will we get? Now the first row multiply by this first column, 1 into 0 1 into 0 plus 1 into 1 plus 1 into 0 plus 0 into 0 and last 0 into 0, and divide by addition modulo 2. Similarly, 1 into 0 second place, 0 into 1 plus 0 into 0 and last 1 into 0 and last is 0 into 0, and divide by addition modulo 2, and last is 1 into 0 plus 1 into 1 plus 0 into 0, fourth is 0 into 0 and last is 1 into 0, and divide by addition modulo 2. What will you get? In that case, 0 plus 1 plus 0 plus 0 0, that means 1 upon addition modulo 2, that means 1 remainder of this is equals to 1. second line 0 plus 0 plus 0, all 0, that means you will get 0 here. And last line 0 plus 1 plus 0 0 0, that means 1 by 2. What was the remainder in that case? That is equals to 101, which is not equals to 0 0 0. That means this implies code A is not correctly transmitted. Okay, similarly you can check code B here whether this is correctly transmitted or not. Let me check. This code B is here only. 1 1 1 1 0 0 1 0 0 0 1 0 0 0 1 and multiply by 1 1 0 1 0. What will you get? 1 into 1 plus 1 1 into 1, that is 2, and again all 0, that means 2 divided by 2, remainder is 0 here. 1 into 1 is 1, and next 1 into 1 is again 2, divide by 2, remainder is equals to 0, and last place 1 into 1 is 1, and all is 1 here. Last is fourth one is 0, that means remainder is equals to 1. This is not also not equals to 0, that means code B is not correctly transmitted. Okay.